All right, so heat from the air transfers to ice and it causes it to melt. So, whoops, went too far. And so melting and freezing, remember that energy can't be created nor destroyed. And so I have two formulas here. And the L stands for latent heat. And so that is kind of the easiest way to put it is that latent heat is kind of like a hidden energy. It's like hidden. So because energy can't be created or destroyed, sometimes when there's an energy transfer, in other words, if we go back to this slide, there is a point where the ice remains ice and absorbs energy and absorbs energy and absorbs energy before it actually melts. Okay? And this is based on the bonds and the molecular structures. So there's a table of these values. Okay? There's a table of these values. And so Q is just heat, and then M is just the mass. And then L is what we call specific heat. And heat is really a measurement of energy. Okay. As we talked about in the last slide. So what we have here in figure for 14.7, for part A, the energy is required to partially overcome the attractive forces between molecules in a solid form, in a solid to form a liquid. The same energy must be removed for freezing to take place. All right. So molecules are separated by large distances when going from liquid to vapor, requiring significant energy to overcome their molecular attraction. Okay, so when you look at the molecules, in a solid, there is an attractive force between the molecules. Okay, and then as heat is absorbed by a solid, what happens is that the heat energy will cause it to melt. And by the way, if you remove that heat energy from the liquid, it will cause it to freeze. Okay? And then you have a similar situation here when you go from liquid to vapor. So you heat this up to boil it, and then when you remove the heat from the vapor, it condenses. That's where condensation comes from. It condenses. Okay? And then there's a table in the textbook that has these latent heats for freezing and for vaporization. All right, so and it's the same value. So we have it in kilojoules per kilogram or kilocal per kilogram. But anyways, I didn't write them all out. This is in the textbook. Okay. So you'll have to look that up to get your homework done. All right, so now this is a graph of temperature versus energy added. The system is constructed so that no vapor evaporates while ice warms to become a liquid. And so that when the vaporization occurs, the vapor remains of the system. The long stretches of constant temperature values from 0 degrees Celsius to 100 degrees Celsius. And then we see the large latent heat of melting and vaporization, respectively. Okay? So here you have ice, you have ice, you have ice. Not a whole lot going on. You can raise the temperature, raise the temperature, raise the temperature. At 100, you have steam, right? But there's this, there's some hidden energy there. It's not a linear function, right? That's what we're trying to say. So let's do an example of this and put it all together. So I actually have this over here, I think. Yeah. So let's do this example and figure this out and see it in action, right? So the question is, let me get my pen ready. You have 3 ice cubes and are used to chill soda at 20 degrees Celsius. The mass of the soda is 0.25 kilograms. The ice is 0 degrees Celsius, and each cube has a mass of 6 grams. Assume that the soda is kept in a foam container so the heat loss can be ignored, right? So you're going to lose a little bit of heat to the environment, the air and stuff. Assume the soda has the same heat capacity as water. Probably doesn't, but it's mostly water. Find the final temperature when all the ice has melted. And so, how do we do that? Well, we pretty much, the ice cubes are melting at the temperature of 0 degrees Celsius. The heat transfer from the soda to the ice will cause that melting. The melting of the ice occurs in 2 steps. The first phase change occurs from solid ice, and it transforms into liquid water at a melting temperature. Then the temperature of the water rises, right? Melting yields water at 0 degrees Celsius, so more heat is transferred from the soda to the water until the water plus the soda reaches thermal equilibrium. In other words, we're going to say that the heat of the ice is equal to the negative, or the loss, of the heat of the soda. Okay? And so then the heat transfer from the ice would be the mass of the ice times the latency heat for freezing plus the mass of the ice times the latency, or wait, let me back up a little bit. We'll undo that one. Times the specific heat times the change in temperature. Right? And then the heat of the soda is equal to the mass of the soda times the latency for freezing of the soda, which we assume is water. That's what they told us to do. Oh, no. I'm sorry. It's the mass of the soda so the heat given off by the soda is just going to be the mass of the soda times the specific heat. And since no heat loss, since we're assuming that all this heat transfer is contained between the ice and the soda. In other words, we're ignoring that some of the air molecules around this container, there's no way it can absorb any of the heat, where the heat transfers strictly between the ice and the soda. And then also, because of that, we're going to say that Q ice, the heat of the ice is equal to the loss of the heat in the soda. Because when you add them up, they should equal 0, right? That's where equilibrium means, right? So Q ice plus the heat of the soda, when you add them up, it should equal 0. So then if you do a little algebra, you get this. So now I'm going to plug all this stuff in. So over here on this side of the equal sign, I'm going to plug in the mass of the ice times the latent heat of freezing plus the mass of the ice times the specific heat times T final minus 0 degrees Celsius. And that should be equal to the negative of the mass of the soda times the specific heat times the change in temperature. Okay, so the only thing I'm doing is this is this, right, which is this, and I'm plugging that in here. Then over here, what I'm doing is I'm saying that the heat of the soda is this. I have the negation of that, so that's how I get this. Okay? So then from there, what I'm really trying to do is I'm going to have to solve for T of F, because that's what I want. Is I want the final temperature in the state of equilibrium. They should be the same. Okay? So that's what we're going to do. Oh, that's a tough one. So let me think this through. I want to get both these. So I'm going to subtract this. Oops. Okay, so undo that, undo that. And so since we're subtracting 0 here, I think, let me push that through. So if I multiply this by this and multiply that by that, yeah, I just get this. And then over here, I have negative M soda Actually, I have to push this through, which is a little crazy. So I'm going to push that through the parentheses. So let me do that real quick. And then I think I have to add this to this side, so I'm going to, yeah, this is wild. So I'm going to add the M soda times the specific heat times the final temperature to both sides. So then over here, I'm going to factor out the TF, because that's what I'm trying to get by itself. And then that would be the mass of the ice times the specific heat plus the mass of the soda times the specific heat. And then this cancels with this. And then that equals the mass of the soda specific heat, 20 degrees Celsius, minus the mass of the ice times the specific heat or the latent heat for freezing. And so then lastly, I got to come back over here and I've got to divide by this. And so this would be the mass of the ice plus the mass of the soda times the specific heat. Then over here, same thing, mass of the ice times the specific heat plus the mass of the soda, CW. Okay, so we're getting there. So then to finish this, I'm just going to plug all that into this right here, this thing here. All right, so the final temperature then would be the mass of the soda times this, which would technically be 0.25 times the specific heat, which is the same as water, which is 4,186 joules per kilogram Celsius times the temperature, which is 20 degrees. And then we would subtract the mass of the ice, which technically is 3 times 0.006 or 0.018 kilograms times the latency heat for freezing for ice, which is 334,000. Okay. And then on the bottom, I would have 0.25 times, and actually because it's the same, we can actually do this a little different. We could factor those out. So I would say, let me think about how I would do this. Yeah. So I could say, I could factor out the mass of the ice and the mass of the soda. So I'm going to put the mass of the soda first, plus the mass of the ice, and then times that by the specific heat for water, because they both had the same specific heat. Okay. And I didn't write the units because I'm running out of space. Normally I'd write all the units out. So then when I calculate all this, and I get the math on this, it ends up being about 20,930 minus, that's a 9, minus 6012, all over 1120, or not 1100, yeah, 1122. And so all that reduces down to 13 degrees Celsius, roughly. Oh, of course it screws up right at the end there, huh? Of course it does. That was a lot. So that's how you would do that. So if I had to recap, if I had a soda that was at, based on soda with a mass of 0.25 kilograms at 0 degrees Celsius, or I'm sorry, at 20 degrees Celsius, and the ice was at 3 degrees Celsius, and I had 3 cubes at 6 grams, that would be my answer. The final temperature for both would be 13 degrees Celsius. And I think that is basically all I had to do. Nope, there's a little bit more. Alright, so we did all that work to say the final temperature of the ice when it melts is, hey guys, I'm recording. Shh, I'm recording, I'm almost done, let me finish this. 13 degrees Celsius. So condensation forms on this glass of iced tea because the temperature of the nearby air is reduced to below the dew point. The air cannot hold as much water as it did at room temperature, so the water condenses. Energy is released when the water condenses, speeding the melting of the ice inside the glass. Ice on these trees released large amounts of energy when it froze, helping to prevent the temperature of the trees from dropping below 0 degrees Celsius. Water is intentionally sprayed on orchards to prevent hard frost. Lastly, direct transitions between solid and vapor are common, sometimes useful, and even beautiful. Dry ice it sublimates, which means it goes directly from a solid to a gas, and it's used a lot for this is an example in figure A. It's used a lot for like stage performances because it's just carbon dioxide gas. And then the last one is frost forms patterns on a very cold window. This is an example of a solid formed directly from a vapor. Okay, so the air molecules that contain water molecules, they can freeze if there's a surface that they can build on, like a substrate. And that's it.